Hi, I'm Phil Pardey. I'm in the Department of Applied Economics in CFANS, but I work out of the Dean's office and in that role am currently Director of the GEMS Informatics Centre, which involves a joint venture between CFANS and Research Computing, which we call the GEMS Informatics Initiative. So Jim Wilgenbush, the Director of Research Computing at the university, and myself co-direct the initiative, and I direct the centre here within CFANS.
And I'm Kevin Silverstein, and I work for the Minnesota Supercomputing Institute, which is part of Research Computing here at the University of Minnesota. And I co-founded GEMS with Phil. It started actually in my driveway, didn't quite make it to our garage, but I spend 100% of my time these days on GEMS.
So we're delighted to be able to introduce you to GEMS Informatics. We've been working to develop a lot of capacity, which we're now just starting to scale up and roll out. And so it's really timely that we've got the opportunity to visit with you and show you the sorts of capacities we've got and to see how we may be able to support you in your research endeavours here on campus. I thought just to give you a little bit of background as to how GEMS Informatics came about 6 years ago, we did some due diligence about the role of the University of Minnesota and CFANS with respect to the 21st century trajectory of innovation in the agri-food space. And we looked at the assets that we had inside the university and the situational assets we had by dint of being in Minnesota, and GEMS Informatics is an attempt to try and harmonise and leverage all of those assets. And so obviously you're very familiar with the great record that an unparalleled record that CFANS has with respect to the Green Revolution, which extends well beyond Norman Borlaug's efforts, includes T.T. Chang, who went off to IRRI, the International Rice Research Institute, and was quite instrumental in the team that helped develop semi-dwarf rice. Perhaps some of you may not be as familiar with George Harrar, who was a graduate of plant pathology here at the University of Minnesota. George Harrar worked for many years for the Rockefeller Foundation. He was the guy that actually hired Norman Borlaug to go and work for the Rockefeller Foundation in the early days back in Mexico. But he was also the president of the Rockefeller Foundation at the formation of the CGIR. And so he helped conceive the idea of international agricultural research and helped bankroll the early efforts of the CGIR. And then finally, Vern Rattan was the first economist ever brave enough to go and work in an agency full of plant breeders out at IRRI. But Vern went on before he came to the University of Minnesota to lead and be president of the Ag Development Council. And so he sat in on the very early, in fact, the inaugural meetings of the Technical Advisory Committee of the CGIR. And so it was very instrumental in helping shape and form the direction of international agricultural research. So by happenstance, we have that great 20th century legacy here at the university with respect to international ag research. We're also, as probably many of you know, home to supercomputers. Controlled Development Corporation released the first commercial supercomputer here in Minnesota in 1964, and then spawned off Cray Computing. The university has lots of linkages into that supercomputing environment, which are now embodied in our world famous Minnesota Supercomputing Institute. And whilst we had some folks probably in the plant breeding group here at Minnesota certainly tap MSI's capabilities, we saw an opportunity to much more strategically leverage the data analytics capabilities of the supercomputer for CFANS purposes and for agri-food research in general. And finally, the direction of agri-food research is definitely towards a more private presence. So my own estimates suggest that over half of the world's investments in agri-food science are done by the private sector. And in the US, it's almost 70% of the total investment in this space is the private sector. So we have to figure out ways to how to engage that private sector. Otherwise, we're going to leave a lot of innovative opportunities on the table, and we're going to under leverage the capabilities of the public and private sectors working together to have an impact in US and global agriculture. And we happen to have the largest cluster of Fortune 500 companies here in our backyard. And again, lots of tactical links between these companies and CFANS and the university. And we were thinking of ways to try and incentivize and support much more strategic relationships to leverage our impact. So GEMS, in addition to sort of being its practical service operation, is conceptually driven by the notion that we can be a leader in the fourth revolution in agriculture, that is the data revolution, standing on the shoulders of the mechanical, the biological and chemical revolutions that went before it, and give CFANS and the university an unparalleled impact in the 21st century, just like we had in the 20th century. So Kevin and I are going to describe the service offerings and give you some illustrations of some of those offerings that will be perhaps more relevant for folks in the plant breeding area. We have 5 service areas. We won't go into all of those in detail. We'll just touch on some highlights of some of those service areas. But our overall mission encompasses the collection, sharing and analysis of data, as I mentioned, to drive the agri-food revolution through data-driven and informatics solutions, not just looking at the problems that are immediately facing us, but looking at the large challenges that we're all familiar with that are now bearing down on agriculture and will affect us for the decades to come. So the early years of CFANS was spent thinking about how we can try and streamline and improve the efficiency of data collection, data curation and data sharing, but to do that in a very intelligent way, as I mentioned, that would be respectful of intellectual property or informal, but nonetheless important data sensitivity issues. And so these obviously impact our roles to engage with the private sector, who have clear concerns about who gets access to and use rights over their data. So we need to think about how we can manage that public-private data sector exchange. But it also affects public research. So you may have pre-publication research that's not ready for sharing or until you get into a publication pipeline. And so we want to be able to give researchers within labs control about who sees what data and who gets what use rights over those data within a lab at the university here, not only within your own lab, but between you and other labs at the university and between you and other labs outside the university with public and private sector. So the mantra in our GEMS platform is whilst we definitely enable and support open data, we facilitate private data, but we're very interested in trying to incentivize pooled data, because we think that purposely pooled data is where we can actually incentivize and support lots of interdisciplinary and novel institutional sort of arrangements for agri-food science. And so our mantra is your data, your choice. So we facilitate a market for data exchange. We don't dictate what that market how that market should operate. And so you get to choose who gets to see and who gets to use your own data assets. So it's built on open source. GEMS platform was built on an open source platform. It sits within a secure cloud within the Minnesota Supercomputing Institute. We actually have a state statute that we had helped facilitate to get passed back in 2018 that designates that any data within the platform is deemed legally private, non-public. That means that data is non-foyable. All the people within GEMS Informatics have HIPAA training, and so we pay a lot of attention to sort of data security within GEMS, but we also have legal privacy, which I think is a unique attribute for us relative to other universities or public agencies in the US. The platform has recently undergone an overhaul, and we just released a new UI for the platform, and so that's out. And essentially the platform allows you to bring data assets together, and it spins up a Jupyter notebook and allows you to then implement analyses on the platform using Python or R code. And as I mentioned, allows you to intelligently share assets on the platform as you deem fit. As an indication of how we think we've gone beyond the rhetoric of public-private research and actually cracked that nut, we are now the platform of choice for the Foundation for Food and Agricultural Research. We support currently 5 research teams, which probably involve approaching 20 or so public-private partners, not just here in the US, but internationally, each working within their own cluster of institutions, and they drive the sharing and use of the data on the platform. One of the key things we support is also metadata management and data quality control. And so these teams are using some of those tools within the platform to help facilitate the pooling of that data with appropriate metadata that then makes that data across the sort of genetics, environment, management and socioeconomic data domains much more functionally interoperable. And in fact, FAR just approached us last week, and we're about to stand up another 2 research groups within our FAR arrangement. So we also support research for big companies like PepsiCo, smaller companies like the Plant Pathways Company, and a host of other activities on the platform. So we're starting to grow our capacity and are now looking to start rolling out usage of the platform across the campus. We also recognised a lot of people spend a lot of time to make data interoperable. They spend a lot of time cleaning up data that hasn't been well curated from the get-go, number one. And number two, we recognised that there was an increasing demand for real-time data to feed into modelling tools within the informatics space within agri-food sciences. So we looked around and spent some time looking at what other sensing opportunities are available, and there are lots and lots of companies out developing sensing tools. But we recognised a niche, and we think it's a really big niche, in this sort of public-private divide in sort of the pre-commercial space, if you will, where we had lots of colleagues coming to us on campus that were looking for a capacity to have a bespoke sensing system that was tailored to their particular research needs. And so we've now been supporting an engineering group within GEMS Informatics for 3 or 4 years now, and we're into our now version 3 of our GEMS logger, which you can see here, and it's a plug-and-play logger where you can configure the different sensing devices into the core logging system that are relevant for the particular research that you want to implement. So, for example, we've partnered with the Research Outreach Centres, and we've now stood up a whole network of networked weather stations across all of the ROCs that consists of a hybrid system between Campbell weather stations and full stack weather stations that we've designed within GEMS. We pride ourselves on that the GEMS weather stations are performing just as well and just as accurately as the Campbell stations, where we have them operating side by side. They cost substantially less than the Campbell stations, and we are getting increasing demand for not just the weather stations within Minnesota, but elsewhere in the world. We have a large project with partners at the University of Stellenbosch, for example, and Venture 37, which is a 5013 spin-off from Land O'Lakes. And we're now deploying a whole suite of GEMS designed sensors throughout Malawi, both on research stations at the National Agricultural Research University, on smallholder farms. I was out there myself earlier this year helping on some of this deployment, and even on commercial farms throughout Malawi. So we now have sensors deployed not just in Malawi and the US, but also in Canada and Norway. And so we have a rapidly growing fleet of sensors. Importantly, there's a back-end quality controlled, quality assured data pipeline. And part of our vision is to have that data coming from multiple sensors that are networked together and get collated so that they're much more readily usable for your analytical purposes. And so the data spins up to the cloud and then can be downloaded as a collection of data across multiple deployments into an integrated database that then can be fed into analytical purposes for your use. Just a quick indication of the flexibility of our sensing system. We have a large project working with folks in Extension across campus to recalibrate evapotranspiration models for a suite of crops, and are well along to building up a new user interface for driving much more data-driven irrigation decisions across the state. That project is supported by the GEMS sensing tools. We're also working with colleagues over in the College of Science Engineering, trying to come up with better methods for calibrating risks from pesticide drift, which has a major regulatory implication in agriculture, and we are using a configurable version of our sensing systems for that project. As I mentioned, we've got sensors deployed throughout Malawi. We're deploying up to, I think, around 65 sensors across Malawi. If you go to the NOAA weather site now, Malawi is currently streaming one weather station at the National Airport in Malawi, and so we're going to have a much more denser set of weather stations across that continent. And we're also working closely with Eric Watkins, who's doing a lot of work on understanding the sort of G by E relationships with respect to turf winter kill, and we have a configuration of our sensing systems deployed on golf courses throughout the US and some into Canada, as I mentioned, Norway, that are helping not just Eric and his research, but are also giving real-time alerts to local managers of those golf courses as to when they may be getting a winter kill event that's developing, that can help them intervene to try and mitigate the effects of that.
So Phil's just described to you both the platform as well as GEMS sensing. What I'm going to tell you is something we call GEMS Exchange. It occurred to us that a lot of people who do data analysis, I think in the plant breeding community, a lot of you program in R. Additionally, a few, it's a much smaller subset, program in Python. But those are the two data languages of choice for data science. And a lot of times when you're trying to grab data, you spend a lot of your time trying to clean up messy data that is out there. You grab it from all these different locations, and inevitably, they're not interoperable with each other. And we try to address this. What we have here within Exchange is streams of data that you can interoperate that are already, a lot of the work was done for you to make sure that they work together. So a lot of what that we've done in the background is we've standardized the interfaces so that when you grab data through an application programmer interface or an API, you grab it in a standardized way. So if I want lat long coordinates, it's always going to be in the same way. If I want to grab certain time intervals, I specified the dates and the years in the same way, as well as a lot of the common variables that might be across. So a lot of it's already been harmonized. We actually have, I'll show you in the next slide, a common gridding for geospatial data, because many of the data sets that we offer are either both, I should say both, temporal and geospatial in nature. And some of it blends public as well as private data. So let me show you in just a sec how we have gridded the data. So what we've done is we've actually thought about the fact that a lot of people want things at a very high level, and others want really down even at the field level or even at that plant level. So we have a grid that accommodates all of this. The grid that we've created, and this has actually been published, you can check reference, just look either for my name or Jeff Thompson or the EASE DGGS, this particular thing, it's the GEMS grid. And it starts at 36 kilometer resolution. And within it, those are the parent cells. Within it, you've got children cells that are each 9 kilometers in squares within that 36 kilometer. And within those, you have 3 kilometer squares, and within those 1 kilometer, then 100 meter, 10 meter, all the way down to 1 meter. Okay, so we can go from 1 meter all the way up to 36 kilometer resolution, which allows you a lot of different scales to operate. And even better, we provide within our toolkit ways to aggregate and disaggregate, go up and down within those resolutions. So we can place things on these grids, and then you can actually get different data streams and actually compare. First, all the data is already projected. You don't have to worry about different projections. So you don't have to be a GIS expert to work with this data. And at the same point, you can also have the same resolution. So everything within the same cells is interoperable with something else and means the same thing as other data streams that are in the same cells. Okay, what kind of things do we offer? A whole host of different things. As a matter of fact, this is already out of date as of yesterday. We actually have 2 more. In addition to what's shown here, we actually have pest risk profiles for a dozen pests each for wheat and maize. We also have actually a market access thing that tells you in the world what is the effective distance to travel to the nearest market of 25,000, 50,000, and so number of people or population sizes. And so, that is literally on the same set of grids that we've just mentioned. Okay, so here we have weather, we have soils information. For the state of Minnesota, we have all sorts of information about the watersheds and catchments and how each stream lands in a particular lake. Then in those lakes, we can tell you every month, dating back to 2018, and in some cases earlier, how the water quality monthly has changed pixel by pixel. So literally 10 meter resolution pixels, how it's changed across every lake in Minnesota over all that time during the cropping season. Additionally, we have information on the crop calendar across the world. Currently, we have LiDAR-based elevation down to 1 meter resolution. But additionally, we're about to put into that a world level digital elevation map, which can tell you elevation across the world at a coarser resolution. And information about land cover. What is the land use across the world in different places? So these are all, as I said, presented to you in interoperable ways. So I should comment, we put a lot of attention into how we did the weather data. We actually looked at a lot of commercial offerings out there for both historical as well as future prediction of weather. And we compared on a variety of different fronts and found what was the best weather, and that's what we provide at GEMS Weather. So this will give you for the last 10 years, effectively daily or hourly weather information at any of the sites that you care about. So all of your field trial locations, for example, dating back at least in the last 10 years, as well as forecasts for the next 16 or 10 days. And in the future, we're going to try to provide a lot of standard data sets that folks like to use, such as PRISM, DayMet, and we will also provide information from the GEM sensors that you've also heard about from Phil. I should comment before I move forward is that you can get access to all this now, okay? If you go to our website, and we'll give you the URL at the end, but if you go to our website, you can just click a button that says, here, I need to fill out this questionnaire about what my research interests are, and then you can have access, and we made that available. So I'm going to tell you about 2 little vignettes about APIs that are coming. These APIs make use of existing APIs that we do. So, we work with our own APIs because part of the motivation for creating these was we're data scientists ourselves, and we want to be able to do analysis. And of course, if there's something we do again and again and again, like the weather or the soils and things like that, we want to actually make that into an API. So all the different analysts within GEMS, use the same root data. So we don't have to explain in 5 different ways the ways that we got the data and say, oh, there was a big flaw in there and a big flaw in there. We can actually come to consensus on what are the best methods. So this particular API that I'm about to tell you about actually makes use of all sorts of things in the background. This is an attempt to do G by E, to actually make predictions about how different varieties of a particular crop. In this case, we started with barley, but we've now moved on to apply it to wheat. But starting with barley, we were interested in could we predict several different yield and quality traits and agronomic traits at the same time that could we predict how it would do in different locations. And as you all know, that's a challenging problem. And a lot of the times in the literature, for yield alone, you would typically see correlation values with observed versus actual predicted to be about 0.7 or so. But we actually achieved between 0.87 and 0.94 for all the various different traits for taking novel germplasm, i.e. the children of the founding populations we trained on, and then planting them into locations they had never been tested. And we had those accuracies with our predictions relative to the actual observed. All right, and these are important qualities, like not just yield, which of course everyone cares about, but also things like the percent protein, which is crucial in barley, because if it's too much protein, then the maltsters can't take that grain because it gums up their processing. Likewise, it's important to be able to know when the heading date is going to be, so you can have consistent harvests and things of that sort. Make sure that they're coordinated, and as well as plant height is an important attribute. So all of these things we're able to predict with very high accuracies. In wheat, which we're doing now with Jim Anderson, the previous work had been done with Jeff Nyhart, pioneered that work with us along with Kevin Smith. This work is being done in wheat with Jim Anderson and Emily and other folks in his group. And those wheat traits that we're looking at, again, grain yield, of course, and protein content for a different reason, but also strength, heading date, again, height, disease resistance. But there are also a bunch of other things, like even looking at the quality of flour and various other traits are stuff that we plan to look into. So I think this would be of great interest to a lot of folks here. We think it's generalizable to other methodologies, and it's definitely something we should talk about. The other one I think is also of interest that we have actually invested a lot of effort in the past, and we're researching now to actually finally put out an API in the next 6 months, is something we call PedTools. And this was developed actually when we worked a lot with CIMMYT and other folks, when we realized that a lot of the pedigrees that they had were either messy, flawed, sometimes they had all sorts of aliases again and again. You see in these particular example here, we have two particular varieties on the left. In this one here on the left, we have the female and of course the male over there. Two different ways that it's been written, with Pembina times 6, meaning 6 back crosses, but in this case PMB was the abbreviation, Thatcher was THA, and this is all caps. You have all these different ways of writing things. For one thing, typical Purdy notation here, but it's not always Purdy notation. You have sometimes arithmetic notation. We can correct for that. For example, soybean folks don't usually use the Purdy notation. And then you have these nested pedigrees that are extremely dense, where they have parentheses. They have, here's an alias, RL4205 is meant to this pedigree, and we can literally parse through, with PedTools, parse through these giant pedigrees and pick out all these relationships. So this is an alias for this particular full thing, that is the parent of this cross, etc. And we can recursively trace through and find all the parents of the parents, and then great-great-great-grandparents, and so on. And that affords us great advantage that we can actually find errors. So if we found in 6 pedigrees that a particular great-great-great-grandparent was identified to be incorrectly in one of them, but not in the other 11 or 12 or whatever, however there were, we can make corrections in a central database. So very important activity to clean up pedigrees. Looking at the genetics in comparison with the actual pedigrees is actually something also very of great interest to us, and maybe is of interest to you. In the meantime, with just the pedigrees, we can compute, we can trace lineages with this package, resolve the aliases, but we can also compute the coefficient of parentage, which gives you an averaged over estimate of what the inheritance value is for each of these germplasm when you're looking at any 2 pairs of varieties. So potentially of use to some of you folks in breeding. Let's talk very briefly about learning. GEMS learning is actually an activity that we picked up with gusto, particularly last spring and a bit into this fall. We've done some, as you see here, out in Malawi, but we also done quite a bit back at home here in Minnesota. We have a lot of offerings as we speak right now. In fact, this last week or two, several have been going on, demystifying the command line with Unix. We're trying to teach folks how to automate tasks using command line languages such as Unix. But in addition, there's been a whole lot in spatial analysis in R, as well as actually just the data science background, data analysis with R. So a lot of different techniques and things that can be trained. I would suggest you check out z.umn.edu/gems-learning, and then you can get this view and find and register for a class. There are lots of choices that you can make.
And we have another one running on pest disease modeling right now as well.
That is true. We do. We have pest disease modeling, especially with a spatial orientation. So if that interests you as well, you should check it out. I'm going to talk briefly about GEMS solutions because that may be of interest to some folks here as well. We've worked with a lot of companies, for example, because they often come to us with custom problems that are not really, any one solution that GEMS offers doesn't really quite satisfy what they need. They need some experts. We have literally, GEMS is made up of over 20 FTEs of folks with all sorts of different disciplines of background so that we can actually help a lot of folks with their problems. Anything that has to do with data science applied to life sciences, really. And so we've had a lot of successes with these folks in working with them. Additionally, we've worked on a variety of different case studies, which many of them were custom operations. So I suggest, again, we're going to give you the website at the end. There's case studies is right at the top toolbar. Take a look at some of these case studies because they really provide quite a compelling example of the ways in which GEMS, I think, is very useful for the agri-food sector. Let's highlight just a few things that might be of interest that aren't necessarily yet advertised so much on our website. So one of them is we've been working quite a bit in the area of trying to use satellite data, try to identify what crop is being grown where. That's a very tricky operation, and a lot of people are trying to do it. I think no one has done it super well. For example, the CDL is an example. Phil, remind me, do you recall what the CDL stands for? I'm blanking. Of course, I think of the Cereal Disease Lab, but it's not that. It's the something layer. I don't know why I'm blanking out, but anyway, there is a common thing that is used by most. I think the USGS puts out.
Crop data.
Crop data layer. Thank you. I keep thinking of our home, the Cereal Disease Lab. It keeps coming to that acronym. That's the crop data layer. Is common, but it has type 1 errors, type 2 errors. There are clearly problems with that, and it's done before the fact, or I should say after the fact, because what would be really useful is to look in the beginning of the season and see how the plants are actually developing and make a call. Oh, that's barley, that's not wheat, and be able to do that from satellite, so that when you're actually doing an economics analysis or something like that, you can actually know what acreage is actually covered by wheat and which is covered by barley on the fly. And that's an area of active research that we are involved in with collaborators as well, in bioproducts and bioengineering, as well as in the engineering school, so computer science. So another area that we are actively working on is looking at the spatiotemporal diversity of wheat particularly, but also looking at other crops. And this is not over a short period of time, but actually looking over the past 100 years. And we have a paper that currently is in its final sets of review, we hope, at PNAS that we're being evaluated. And we hope that goes forward. And additionally, I should say that we're doing a fair amount of work on using natural language processing to take the huge troves of information that's on the internet that describes in gory detail all the information about particular varieties of your favorite crop, and trying to pull that into a central database that you could mine, and you could actually see, where was the evidence from? Do I believe it? And just amass it into one area is what we're trying to do with this natural language processing parser. And we have some successes there, and we hope to be able to roll that out sometime in the not too distant future as another API for you to look at. I think that really covers the information we wanted to share with you. Here is the website. It's pretty straightforward, especially if you're at UMN. It's just gems.umn.edu. And you can see all of our 5 services. You can see a lot of the case studies I mentioned, who the people are involved, and contact us is critically important. Or you could contact me directly, cats@umn.edu, or Phil.
Or Phil at pparty@umn.edu.
Right. We look forward to talking with you folks. Actually, here, let me stop the share. We look forward to talking with you folks. It'll be very short now, and I hope there's a lot of discussion.
Yeah, and I think, as I mentioned at the top end of the talk, it's a critical stage for us. We're looking to roll out the services more broadly across the campus and elsewhere. And so we really value your feedback, because we try to be user-driven and direct the efforts that we do to have the maximum impact for the community that we're embedded in, which is you folks. So we look forward to the follow-up conversations.
Thank you so much.
Bye.